Boundedness. Consider a set S containing the elements 1, 2, 3, 4, 5, and 6. We can bound the set below by 0 or above by 10, forming a ceiling and a floor to the set, so that S has a lower bound 0 and S has an upper bound of 10. Why are lower bounds and upper bounds important? Consider the question, how much is a loaf of bread? And the answer, less than 1,000 rand. Or the question, what grade is required to pass a module? With the answer, more than 25%. 1,000 rand provides an upper bound to the price of a loaf of bread, whilst 25 provides a lower bound to the passing grade of some module. Pretty useful information. More formally, a subset S of the real numbers is bounded above if there exists a real number m such that m is greater or equal to every element x of the set S. The number m is called an upper bound of S. Similarly, a subset S of the reals is bounded below if there exists some real number small m such that it is less or equal to every element of the set S. This number small m is said to be a lower bound for the set S. Or simply, we can say that the set S is bounded, generally used to mean both bounded below and bounded above. So, bounded above means the set is capped above, bounded below means the set is capped by some number below, and bounded means the set is captured in an interval that is captured by some number small m and big M on both sides. So, as we remember, bounds give us some information as to the upper bounds of things, upper limits of something such as the price of a loaf of bread, or the lower limit of something like a pass mark. However, the answers of a loaf of bread having an upper bound of 1,000 rand and a module's pass mark having a lower bound of 25% aren't very satisfactory or useful answers. Better answers to these questions may be that the price of a loaf of bread is at most 20 rand, or that a passing grade for some module should be at least 50%. These are more practical answers and they're actually closer to the truth. Let's have a look at the concepts of minimum and maximum. The minimum of a set S is an element of S that is less or equal to every element of S, while the maximum of S is an element of S that is greater or equal to every element of S. We note that the minimum and the maximum are in fact lower and upper bounds. However, these are in some sense the best of the lower and upper bounds. A comparison between the concepts of upper and lower bound and minimum and maximum. We'll recall the definition of an upper bound as an element m which is greater or equal to every element x of S, and the maximum or a maximum of S is an element x0 of S that is greater or equal to every element of S. Notice that a maximum x0 of S is an upper bound of S. Further, maximum x0 is an element of the set S. An upper bound M need not necessarily be an element of the set S. This is what distinguishes an upper bound from a maximum, and similarly a lower bound from a minimum. That is, given all the upper bounds of a set S, amongst them there is a maximum or a best upper bound. Let's have a look at another set, S0, an infinite set. The set of all fractions 1 over n, where n is a natural number. Looking at the set from above, we notice that it's bounded above by a number as large, say, as 100, and in fact, it's actually bounded above by any real number greater or equal to 1. An upper bound in the set is 1. As we can see, 1 over 1 is 1, so 1 is actually in the set, thus making 1 the maximum of the set S2. From below, we notice that it's bounded below by, say, minus 100. In fact, the set S2 is bounded below by any real number k less or equal to 0. Now, a lower bound in the set. We notice that unfortunately 0 is not an element of S2. Thus, 0 is not really the minimum of S2. So, what is 0? As 0 seems to be the best candidate for such a position. To see what 0 is, let us recall the definition of a lower bound and the minimum. A lower bound is an element m less or equal to every element of the set S, while the minimum is a lower bound that is an element of the set S. However, 0 not being an element of the set S implies that it cannot be the minimum, but it is indeed a lower bound, as stated before. So, what exactly is 0 to S2? And if it's not the minimum, what is the minimum of S2? Let's try and find out what the minimum of S2 is. The minimum of S2 is an element of S2 that is also a lower bound of S2. For argument's sake, suppose that the minimum small m of S2 did exist. We'll just figure out what it looks like later. Being an element of S2 would imply that it is 1 divided by some natural number n naught. Being a lower bound would imply that the minimum 1 over n naught is less or equal to every element x of S2. That is, it's less or equal to 1 over n for every natural number n. Now, when we say for every natural number n, we really mean for every natural number n. This is a universal statement, so there cannot be any single natural number n which violates this lower bound condition. So, to emphasize, let's actually check if this is indeed the case. Suppose n is less than n naught. Then the computation below shows that indeed we do find that 1 over n is greater or equal to 1 over n naught. However, n could be equal to n naught, in which case we find that indeed 1 over n is less or equal to 1 over n naught, mainly because the inequality in the lower bound condition is not strict inequality. Now, for n greater than n naught, we sadly find that 1 over n is less than 1 over n naught, which violates the lower bound condition. So, our argument seems to have failed. But in every step, we used totally valid arguments. So how did we fail? Assumptions. We did make one assumption, that is, the existence of the minimum m of s, S2. So, since from a true assumption, one can only get a true conclusion using valid inference rules, we can conclude that our assumption that the minimum of S2 actually exists was actually false. So the minimum of S2 does not exist. So, what then? This is where the concepts of infimum and supremum come in. Given a non-empty subset S of the real numbers, the infimum of S, denoted inf S, is the greatest lower bound of S. The supremum of S, written sup S, is the least upper bound of S. So, infimum and supremum are related to lower bounds and upper bounds, which, as we saw before, were related to minimum and maximum. So what's the difference? Let's have a closer look at the relation between the greatest lower bound, the infimum, and general lower bounds and the minimum. Recall that a lower bound, small m, is an element of the reals which is less or equal to every element of S, and that the minimum of S is an element x naught which is less or equal to every element of S, and that the difference between the minimum and a general lower bound is that the minimum is a lower bound that is in addition an element of the set S, whereas a simple lower bound need not be an element of the set S. Now the infimum is the greatest lower bound of S. That is, given any lower bound, small m of S, the infimum is greater or equal to that lower bound. Notice too that the infimum of S need not necessarily be an element of S. It is simply that it is a lower bound and additionally the greatest of the lower bounds. Now, being the greatest lower bound would mean that you are kind of the best lower bound. But we said that the minimum is the best lower bound. Isn't this a bit of a contradiction? We can't have two bests. No, we can't have two best lower bounds. We can't have the infimum being the best lower bound and the minimum being the best lower bound. There has to be one best. In fact, if both the minimum and the infimum exist, we find that the infimum is equal to the minimum. Thus, there is no contradiction in the existence of both the infimum and the minimum, or the idea of both the minimum and the infimum being the best of the lower bounds. So, if a set is bounded below, then there is a set of lower bounds. One can create the set of lower bounds of the set, and amongst the set of lower bounds, there is one which is the greatest lower bound, and that is termed the infimum. And additionally, if that element is an element of the set itself, it is in fact the minimum. Similarly, if a set S is bounded above and a subset of the reals, it has a supremum, and if that supremum is indeed an element of the set itself, it is actually a maximum. So, sounding a bit repetitive, a final remark, we start off with a set S of the reals, and we determine whether it's bounded below, or bounded above, or bounded from both sides, both above and below, or it may be unbounded or not bounded. If indeed it is bounded, say below, one has a set of lower bounds of the set S, and amongst these lower bounds there exists an infimum of S, which is the greatest lower bound, or one can think of it as the best of the lower bounds, and the existence of this infimum is guaranteed to us by the completeness axiom. And furthermore, this infimum may or may not be an element of the set. However, if it is an element of the set, we find that it is in fact the minimum by the theorem which says that the minimum is equal to the infimum if both indeed exist. However, one could find that the infimum exists but S does not have a minimum.